This video is over section 17.1. Let's start with the vocabulary for this section to make sure we have a good understanding of the words that will be used. A relation is a set of ordered pairs. A function is a special relationship where each input has only one output or has a single output. So I want you to think about a machine. If you have a machine that when you put wood in, you get a chair out, and every single time you put wood in, you get a chair out, that's the function of that machine, is to create chairs. If all of a sudden you put wood in and you got a toothpick, then that machine is no longer functioning. It's not a function. So you have, anytime you have an input, you have a single output. So that machine, the output would be a chair when the input is wood. Okay? All right, function notation. This is what you're going to see. We pronounce this f of x. And basically, it's the name of a function with x as the input. You could see g of x, h of x, j of x, p of x, q of x. You could name that function whatever you want. When we talk about functions, it's important to understand the domain and range of a function. Your domain is your set of inputs, or x values. While your range is your set of outputs. Or y values. Okay, now that we've covered the vocab, let's talk about how to evaluate some functions. Okay, so notice at the top of this section, it says equation y equals 5x plus 3, function f of x equals 5x plus 3. These two things say the exact same thing. The function is just named differently. F of x means the same thing as y. Okay? All right, so let's take a look at, let's just explore function notation just a little bit further. We're supposed to evaluate these functions. F of 3 means plug 3 in for x. So if I'm finding f of 3, I'm looking at function f, so this guy right here. Everywhere I see an x, I'm going to put a set of parentheses in place of the x, and this is what goes in those parentheses. Then you would use order of operations to solve from there. Well, order of operations tells us to do the squared first. So we have 9 minus 3 times 3. Then we're going to do our multiplication. So 3 times 3 is 9. So 9 minus 9. And finally, we do our subtraction. So f of 3 equals 0. A lot of people want to divide here by 3 just to get rid of the f of 3 part. Don't do anything. This is 0. This tells us that when we input 3 into f, we get 0 out. G of 3 is going to be the exact same way, only what function do you think we're going to plug it into? That's right, we're going to plug it into G. So everywhere we see an x and G, we're going to put a set of parentheses. We're going to plug that number in. We have 2 times 3 minus 1. We're going to do our multiplication first. So 2 times 3 is 6, minus 1 would be 5. So that tells us when we input 3 into G, we get 5 out. D says f of 3 plus g of 3. So we would find f of 3 and we'd find g of 3 and we'd add them together. Well, examples A and B, we already found f of 3 and g of 3. So let's just add those together. F of 3 was 0. g of 3 is 5. 0 plus 5 is 5. Take a look at E. Find f of negative 2 plus g of negative 1. Well, we haven't done either of those, so we have to start with that. F of negative 2. Notice I'm keeping that negative 2 in parentheses. That's really important. Negative 2 squared is 4. Okay, now we have 4 minus 3 times negative 2. We'll do the multiplication first, so 4 plus 6. Finally, we're going to add. All right, let's take a look at some other things about functions. There's a couple different representations of functions. To demonstrate, we're going to use the function f of x equals 2x minus 1. Now this is the equation representation of a function. The other ones we have to do a little bit of work to find. So in order to fill out a table for this, let's start by putting a 0 in the middle. And then if x had a fraction attached to it, we would use different numbers, but since it doesn't, we're just going to do 1, 2, and negative 1, negative 2. Now each number I'm going to plug in for x. So 2 times negative 2 minus 1, negative 4 minus 1 is negative 5. Negative 1, so 2 times negative 1 minus 1. Negative 2 minus 1 is negative 3. Two times 0 is 0. Minus 1 is negative 1. And then we can kind of see a pattern emerging here. We're going up by 2, up by 2, up by 2. So I can go up by 2 again, up by 2 again, and that pattern should stick. Now we know from previous units that this is going to form a line because 2x minus 1 is like mx plus b. So let's go ahead and plot our points and we'll see what kind of line this makes. So we have the point negative 2, negative 5, negative 1, negative 3, 0, negative 1, 1, 1, and 2, 3. We just connect our points and that's our line. So that's a graph representation. And a mapping basically just takes our x values and it maps them to a y value. So what I like to do, I'm going to put my x's over here, my y's over here. I like to put my x's in numerical order. So negative 2, negative 1, 0, 1, and 2. And I like to put my y's in numerical order as well. And then we just map what goes with what as we do the arithmetic. Negative 2 goes to negative 5, negative 1 goes to negative 3, so on and so forth. And we're just basing this on our table that we found out earlier. So that's what you're going to be doing as well. Alright, determining whether a relation is a function. Remember the story I told about the chair being created by putting wood in the machine, and that's the function of the machine? So we have to figure out whether or not the machines that we're exploring function. So it says for a table, set of ordered pairs or mapping, does each input have only one output? For a graph, do the vertical line test. If no vertical line can be drawn that will intersect the graph more than once, then the graph is a function. If the vertical line intersects the graph at least twice, the graph is not a function. Okay, so let's talk a little bit about that vertical line test. If I am drawing a vertical line on an xy axis, notice that every single point on that line has the same x value, but every point, most of the points have different y values. So if you draw a vertical line, and let's say here's your graph, it touches two different places. For x value of 4, we have two different outputs, which means it is not a function. If it's a function, when we plug something in, we always know we're going to get the same thing out. That's why it works. Okay, take a look at example 2, and we'll talk about how to determine whether or not these are functions, and then we'll look at some graphs. So on number 2, I want you to start by looking at the table. Are there any x values that appear twice? Well, yes, there's a couple, 2's. So then we're looking at the y values. If they're the same, we're okay, but if they're different, that means we have a different output for the same input. Well, look what we have. 2 and 6 and 2 and 4, which means the outputs are different, which means it's no function or not a function. Okay, same thing with B. Look at each one of your inputs which are on the left. Are any of them being mapped to the same, or to, different outputs? So if we only have one of each input, that means they can't be going to different outputs. So this would be a function. And then on C, same thing. Look for a repeat in your x values. We have -2, 1, 3, 5, and 7. It looks like they're not any repeats, which means it is a function. All right, last question, determining whether or not a graph represents a function. So we're going to use the vertical line test as we were talking about a few minutes ago. Look at your graph and try to imagine if there anywhere that would have a vertical line that touches the graph more than once. Well, on this particular example, 3A, the answer is no. But on B, look, several different vertical lines would hit twice on the graph, which means that this is not a function, whereas A was one. So take a look at C. Is there any problem areas? We have a line here. All right. None of those lines are going to touch the graph more than one time. None of them are going to touch more than one point. That means, yes, it is a function.